Watch this image form from a random pattern through many small changes, where each change depends on what the picture looks like at that moment. But during learning, the model never sees this full sequence, because each example shows only one moment and the change needed at that moment. So how can these separate examples teach the model every change needed to create the final image? To answer that question, we first need to see what the model must learn. These are real handwritten digits from MNIST. Each image has 28 by 28 pixels, so the model reads it as 784 numbers, and we show it as 1 point on this flat view. The blue points come from random patterns, while the orange points come from real digits. We do not pair each blue point with one chosen digit. We only need the blue group to end with the same shape and crowding as the orange group. This pattern of where points gather is called a distribution. To change this distribution, the model must answer one question for every possible picture at every moment. Which way should its point move, and how fast? We draw that answer as an arrow. The complete set of arrows is called a velocity field. The equation on screen says that the model reads the current picture and moment, then returns its arrow. If random points follow these arrows, their distribution moves toward the real digits. The separate examples we saw must teach these arrows one at a time. But where can we get the arrow for each example before the model has learned the field? Here's how we can create one arrow before the model has learned anything. Choose a random starting pattern and a real digit independently, then call them x0 and x1. They make one example, but the random pattern does not belong to that digit. Draw a straight line between them and choose one moment where t equals 0.37. The picture at this moment is 37% of the way from x0 to x1, so we calculate it from 63% of the starting pattern and 37% of the digit. This gives the picture directly without calculating any earlier picture. As t moves from 0 to 1, the point travels along the full line, so the correct direction and speed are x1 minus x0. The model receives the picture and its value of t, predicts an arrow, and compares its answer with this known arrow. Repeat with a new pattern, digit, and value of t. This method is called conditional flow matching because each correct arrow depends on its chosen pair. We can now make as many examples as we need. But two different pairs can place points at the same position and moment while giving different correct arrows. Which arrow should the model learn? We can answer that with the two arrows already on screen. Keep the moment fixed at 1/2. One chosen pair gives the arrow 6, 2 and the other gives 6, -2. Both examples show the model the same point and the same moment, but the model does not see which pair produced that point. It must therefore give the same answer for both. Training measures the square of the difference between the model arrow and the correct arrow. For the left to right part, both correct arrows are 6, so the best answer is 6. For the up and down part, one answer is 2 and the other is -2. If the model chooses 2, the two squared differences add to 16. If it chooses 0, they add to 8. 0 is better, so the best single arrow is 6, 0, which is the average of the two correct arrows. Now include every pair that can create the same point at this same moment. An arrow that occurs more often appears in more training examples, so it has more effect on the answer. The equation on screen states the result. Among all pairs that can create the current point at the current moment, the model learns their average arrow. It does not include arrows from other points or other moments. Apply this rule at every point and every moment, and the model learns one arrow everywhere. Together, these arrows form the single velocity field we need. Averaging the arrows does not ruin the change from random patterns to real digits, because the goal is to match the full group, not to copy each straight line. At each point and moment, the average arrow gives the same combined movement as all the training arrows that occur there. When this is true everywhere, the generated group has the same shape and crowding at each moment as the group on the straight lines, even though each generated point can follow a different path. During learning, each example teaches the model one arrow for one picture at one moment. To create a new image, the model starts with a random pattern and follows one predicted arrow after another from the first moment to the last. During learning, choose one random pattern, one real image, and one moment. These choices directly give the picture at that moment and its correct arrow, which we compare with the model's answer. No earlier picture is needed. Creating an image is different because there is no chosen final image. Start with a random pattern, ask the model for an arrow, move a short distance, and ask again with the new picture and moment. Repeat until the last moment. This is why learning in flow matching is called simulation-free. Each learning example is calculated directly without following earlier arrows. The name applies only to learning because creating an image still needs repeated steps. For one step, let the moment increase by an amount called delta t, multiply the current arrow by delta t, and add the result to the current picture. This update is called Euler's method. A smaller step asks the model more times but follows changes in direction more closely, while a larger step asks fewer times but can move too far in an old direction. So why can the direction change when every line used during learning was straight? The direction changes because the model does not follow one yellow line from beginning to end. At its current point and moment, it uses the average of all training arrows that can occur there. After it moves, a different group of training lines can pass through the new point, so their average can point in a new direction. Repeating this change makes the green path curve, even though every yellow line is straight. This also explains the error from the large step. Euler's method uses one arrow for the whole step, so a large step continues in that direction after the correct arrow has started to turn. Smaller steps ask the model for a new arrow sooner and follow the curve more closely. They can be more accurate, but they require more model calls. Some turning comes from how we choose the starting pattern and real image for each learning example. If we choose them independently, many straight lines cross, and the correct arrows near those crossings can disagree. We can instead choose pairs that produce fewer crossings, so the arrows agree more often. The rule for choosing these pairs is called a coupling. Changing the coupling can reduce turning, but it does not guarantee a straight path. Stable Diffusion 3 uses this same structure at a much larger scale. With that connection in place, we can now put the complete process together. Choose a random pattern, a real image, and one moment. The straight line between them gives the picture and correct arrow at that moment. Repeat with many pairs and moments, and the model learns the average arrow for every picture and moment. To create an image, start with a new random pattern, ask the model for an arrow, move a short distance, and repeat until the last moment. This is flow matching. Many separate examples teach one complete set of arrows that turns random patterns into new images.